Hello and welcome back. Before we go ahead and solve a few more problems, let's sort of look at our problem solving methodology. So, what we are going to do in the problems which we solve is to go through these steps in some fashion iteratively more than once and identify what we know. So, what we would first do is to see whether there are one or more systems or control volumes which are there. So, should we treat it as a system or should we treat it as a control volume? That is the first thing we will identify. So, we will identify whether there are any forces acting which we know, and consequently whether there is any work interaction. Do we know the directions of it? Is there any heat flow and the directions of those if we know all them? Then we will try to identify what we know about the initial state. So, do we know the pressure or temperature or internal energy or entropy, or what do we know about the initial state? And we will keep in mind that if we are dealing with only like say pure compressible substances, then it is sufficient if we know two of the properties, then we will know everything about the initial state. That is of course considering that we do not have motion and kinetic and potential energies involved. We will look at what is the thermodynamic model, which tells us something about the property relations. So, is it an ideal gas where we have a relation PV is equal to mRT? Is it, for example, something like say steam, where we can use tables, which we will look at a little later on? Is it a real gas where we can use other relations or we can use the compressibility charts? This is something which we will decide. Once we know this, then we know how to calculate properties. Then we will see what we know about the process. So, is there something constant? For example, is pressure constant and is it an isobaric process? In which case, knowing the initial state and knowing pressure is constant, we know something about the final state. Is temperature constant? Is volume constant? Is anything at all constant? Or in case things are varying, do we know how they vary? So, that is something which we will try to find out. So, we will see what we know about the process. Is there something constant, or do we know how the process is happening? Do we know how things change? That is something useful to know. And knowing the initial state, something about the properties and something about the process, it should be possible for us to usually find out something about the final state. Or in some cases maybe we know the final state, but we do not know the initial state. So, using these going through this a couple of times may give us something about the unknown state. We will usually try to draw a diagram, either a PV or a TS or a pH or any of those diagrams between two properties, which usually helps. In some cases it may not help. So, we will try to find out if a diagram would help, and if so, what kind of a diagram would help, that we will try to find out. And then we will use the first law of thermodynamics, essentially conservation of energy. We will see that we will also need to do explicit mass conservation when we are looking at volumes, control volumes instead of using systems. And in most cases, at least for the simple problems, this should be sufficient, but there could be problems which are not close and we may need trial and error to find out a solution. We will maybe look at one or two examples of this sometime during the course. The problems which we will look at will have closed form solutions, so this may not be necessary. But if we go towards real world problems, we may not have analytical expressions which we can solve easily, and that of course we would do iteration and do trial and error to find out solutions. And we may need to go through this process more than once for a problem, because maybe we will find something here and then go back and use it and put it in some other place and come through it. So, that is essentially how we are going to solve problems. We will go on to another problem now. So, this says as a DC electrical motor which is used to operate a hoist mechanism in a crane. So, we can draw some kind of a motor. And this is going to operate a hoist mechanism. So, we have some kind of a pulley and we have a rope, and this is going to lift some mass. So, the motor is supplied with 300 volts and 10 amps from a DC source. So, we have some kind of a battery. Which is connected to this motor, and what we know is that this provides 300 volts and 10 amp of current, and this is connected to this motor. So, because of which the motor spins, the torque provided by the motor to the hoist shaft is 250 Newton meter at 50 rpm. So, the output from the motor is 250 Newton meter at 50 rotations per minute. What we also know is that this happens for 2 minutes, and the hoist mechanism lifts a mass of 2.5 tons. So, a ton is 1000 kg. So, 2.5 ton is 2500 kg through a distance of 5 meter. So, let us say this is a center of gravity point, and later on let us say it moves to this point. So, finally the mass would be here. So, we are asked to find out the work interaction for the DC source, the motor, the hoist and the mass. So, we are asked to find out all of these. So, if we look at what is happening over here, so we have this battery which has energy. The battery is giving out energy and doing work. So, the battery is doing work on this motor, it is making the motor to spin. So, the work interaction for the battery would be positive, it is doing work on its surroundings. The work interaction for the motor would be negative with respect to the battery, because battery is doing work on it, because current is going in and coming out, and the motor is in turn doing work on the hoist. So, that work interaction would be positive. So, we have negative work from this side, positive work from this side. Now, this hoist is getting negative work from the motor, and it is doing positive work in lifting a weight. And as far as the weight or mass itself goes, the weight is being lifted. So, the interaction for this weight is also negative. So, these are all the interactions which are there. So, what we need to do now is find out the magnitudes of them. So, we can look at initially the work interaction for the battery, because that is possibly the easiest to do. So, the voltage into the current, it is DC voltage and DC current, would give us the power, into the time would give us the work interaction. So, this is 300 volt into 10 amp into time is 2 minutes. We are going to use SI units as usual. So, this is 120 seconds. So, we have 3 12s as 36, and then we have 3 zeros. This is the work interaction for the battery. It is positive for the battery because the battery is doing work on its surroundings. So, next what we can look at is, we can look at the interaction for the motor. So, the motor is getting work done on it by the battery. So, it will have negative work done from the battery, and then it is doing work on the hoist. So, the work done on this motor due to the battery, we have already found out, it is 36,000 joules. So, this is minus 36,000 joule. And if we look at what the motor is doing, okay, I think I have missed out one zero here, which is being pointed out. So, yeah, I have another 0. So, that is essentially 360 kilojoule. So, let me write that as this. And as far as the work interaction from the motor out, so the motor gives 250 Newton meter at 50 rpm to the hoist. So, the work done by the motor on the hoist would be given as T theta. So, the torque is 250 Newton meter, and omega, or the Maybe I will go on to the next page. So, the work from the motor to the hoist would be given as T theta. The torque we had earlier as 250 Newton meter, and the speed is 50 rpm. We have n, which is the speed in rotations per minute, is I think 50 rpm. So, that is 50 divided by 60 rotations per second. So, the power would be given as 2 pi times n into the torque. So, that is 2 pi into 50 by 60 into torque is 250 Newton meters. I can cancel out 0. So, I am going to use my calculator. So, that is 2 into 3.1415 into 5 by 6 into 250, which is 1308.9 watts. This can also be written as power into time. So, T over here is this 250, theta is essentially 2 pi n times time. I haven't put in the time yet, so I have rewritten it in this fashion. So, now I can write this as 1308.9 into the time was 120 seconds. So, I get this value as 157 kilojoules. This is the work from the motor onto the hoist. So, let me just call this the same thing here, work done by the motor on the hoist. So, the total interaction for the motor is whatever the battery does on it, which is minus 360. Plus whatever the motor does on the hoist, which is plus this, which gives me a value of minus 203 kilojoule. Net interaction for the motor is negative. So, what we see is that the battery is doing a lot of work on the motor is doing a smaller amount of work on the hoist. So, then the question is what happens to the remaining? So, clearly the rest of it goes into increasing the energy of the motor, which possibly means that the motor is getting heated up, it has friction, it is getting heated up, and then that remaining energy will finally get dissipated as heat, which is what we also see. So, for example, if you have a fan, it has been running for a while, after you switch it off, if you touch it, you will find that it is warm, because not all of the electrical energy which it gets is being converted into mechanical work. Some of it is getting dissipated later on as heat. So, we have found out the interaction for the motor. We also need the interaction for the hoist. So, for the hoist, we have work being done on the hoist by the motor, and then we have the hoist doing work on a mass, it is raising the mass. So, work being done on the system is negative. So, if we take the hoist as a system, whatever work is done on the hoist is negative. So, that is essentially the work interaction with respect to the motor. We have just calculated that here. So, we would have minus T theta, which is the work done by the motor on the hoist, and we have plus mgh, which is the work done by the hoist in lifting up the mass. So, the value of T theta, or I can also write this as minus power times time plus mgh. I have already found out this value, it is 157 kilojoules. So, I have it as minus 157 kilojoule plus mass of the object which is being lifted up is 2.5 tons. Acceleration due to gravity is 9.81 meter per second square into the height by which it's lifted up, if I remember right, is 5 meters. So, this is plus 122.6. So, this comes out to be about minus 122.4. I think I didn't do that right. That this comes out to be minus 34 kilojoule. And then we have the work interaction for the mass itself. If we take the mass as a system, the mass is being lifted up, so work is being done on the mass, so that work would be negative, and the work done would be essentially the weight into the displacement. So, that is minus 2500 kg, sorry, minus is outside, it's 2500 kg is m, into 9.81 is g, into 5 meters. So, this should be this value here. Which is the work interaction for the mass. So, what we should also see is that if we add up all the work interactions, we have seen earlier that the sum of all of the work interactions should be 0. So, we can check whether that is indeed true. So, we had the work interaction for the battery, which is 360. I am going to write all of them in kilojoules. Then we had work interaction for the motor, which was here, which is minus 203. We had work interaction for the hoist, which is minus 34.4, and for the mass, which is minus 122.6. So, if we now add up all of these, so we have 203, this is 325 and about 35. So, we get 0, which is what we were expecting to get. So, if we add up all the work interactions, sum of all interactions should be 0, provided we taken into account all the interactions which are there. So, we see that that is indeed the case.